Okay, next up. APC, Calc review on E&M, electricity and magnetism. We're going to go through all these together. Take a look at the videos that were put together for APB, because pretty much all the stuff that applies to them is still stuff that won't hurt you to be familiar with. You can still do very well on the APC exam, even knowing just that as a basis and being able to sprinkle in some of your calculus relationships. Speaking of calculus relationships, some of the most important, and these can actually be re-derived from some of the stuff that I gave you before. Remember that work equation? It was work equals the integral of f dot dx, right? And I told you in the electricity and magnetism, the electrostatics one, that you should always remember this one, that force equals our electric field times Q. And also that our potential energy equaled our voltage, our potential, times Q. Okay, well, work equals negative potential energy. So this would become potential energy equals negative integral F dx. That's this relationship here. Brings in that negative. Pardon me. All right, and now I'm going to apply both of these at the same time. I'm going to divide both sides by Q. My potential energy divided by Q gives me my potential. And my force divided by Q gives me my electric field. First, and one of the most important equations, and again, if you know the relationships that I told you before were important to keep track of, you can derive it at the drop of a hat. Our potential is going to be equal to negative integral E dot dx. Don't lose track of the fact that this is in fact a dot product. Gets rid of our vectors. These guys are vectors. This guy is a scalar. Still very important. This is the integral form. The differential form, you just kind of move things around and you'll find that it is E equals negative dV dx or dr. It's a derivative with respect to distance, some displacement. All right. These are key calculus relationships. Make certain that you're comfortable with those. Next up, something that we spent a good amount of time on, so hopefully you're very comfortable with. If not, double check what we've done, because this is one of the big ones. Gauss's law. This is about finding the electric field from a given source. Looks like this. E dot dA, again, dot product. And again, A, our area vector, we talked about that one, equals charge enclosed, make certain that it's only the charge enclosed, divided by epsilon naught. We had the light bulb under the mason jar as a good example of why it has to be enclosed, because if it's not inside of it, whatever the flux coming in is also equal to the flux going out. And that's for stuff that acts like the electric field. When it comes to Gauss's law for magnetism, it turns out it's always zero because they always are closed loops. All right. This one is based heavily on symmetries. We often use spherical, which oftentimes would simplify down to forms that you recognize with Coulomb's law. Again, there are reasons that we look over Coulomb's law, even though it's very limited. Spherical. Cylindrical, which is a very popular one because that's very similar to our wires and applying charges onto those. And then finally we had planar symmetry, where we could use rectilinear things like cubes or boxes, but we could only use them as our Gaussian surfaces on planar things. So we could have used that on the parallel plate capacitors, though we ended up using cylindrical on that, kind of to the same effect. Symmetries are an important idea in Gauss's law because we need to try and make it where our electric field is constant through our surface so that we can pull it out, because we're not doing multivariable calculus, and honestly having to evaluate that for a real thing could, or a non-symmetric, that's still plenty real, a non-symmetric can get very unpleasant very quickly. Next up, equations. I thought I was doing these in blue. I was, but then I got switched up somewhere in there. I apologize. We'll stick with red. Current is dq dt. And again, whenever I use q, other people may use a capital Q instead. Doesn't really matter, but Q is kind of the standard for charges. I prefer the little q because I use capital Q for a couple of other things. dq dt. This is an important one because this is where pretty much all of your differential equations for circuits are going to come from. Well, at least for an RC circuit, for resistors and capacitors, this one's going to be very important. For the capacitor, you'll have a relationship with Q itself. Q equals Vc. Check the other video. And then as you do loop rule across them, you can set up an equation where you have voltages with your, just like we saw with the drag equation, you'll end up with some value and a differential equation where, so we did this when we derived, actually the next thing I'm going to write, which is the equation for charging a capacitor. Charge as a function of time equals Q naught, and here I go using the capital Q, so I apologize. 1 minus the exponential function raised to the t, where t is your time in seconds, divided by tau, where tau is our time constant, which is RC. We've talked about that. The units ohms times farads returns the units seconds. And our time constant gives us an idea about how long it takes to charge the majority of our capacitor. Remember, in time equals RC equals our time constant, tau, we'll charge approximately 63% of that capacitor. By the time we get about 2 or 3 time constants, the capacitor is, for all intents and purposes, pretty close to completely charged. Though technically, with this exponential function, it requires an infinite amount of time to charge completely. We derive this by setting up with loop rule. We have the voltage of the battery minus the voltage across the capacitor, Vc, minus the voltage across some resistor, equals 0, closed loop. So we ended up doing some tricks on this to get this replaced with our capacitance. Double check your notes on that. But the important thing on that is we'll have some value that we can play around with and move around. Vc, so our voltage across the capacitor. From Q equals Vc, we know that our voltage is actually going to be equal to Q, let me do capital Q actually, divided by our capacitance C, minus the current across, or I'm sorry, the voltage across the resistor, which is IR, but I is equal to dq dt. So we end up with an equation that looks like this. Minus Q, I'm using the capital Q. This is why I hate having to switch between the two. Can't believe I made that slip up. Minus dq dt r equals 0. In fact, it was when applying specifically this that we derived this equation and we saw our time constant develop up here. Okay? So that's that guy. Next up, Amperes Law. We'll talk a little bit about inductors in class. That's one of the other ways that you can end up with differential equations in circuits. But right now let's take a look at some of what we need for magnetism. So Amperes Law. Stated as follows: closed integral B dot dl. This one is not a surface area integral. It is just integrating around usually a loop. Oftentimes it's a circular loop, though sometimes we've used a square loop depending on our geometries. Equals mu naught current enclosed. Now from this, we dealt more and more with the idea of J, which is our current density. And our current density is pretty much our current enclosed divided by our area enclosed, or our total current divided by our area, our total area. So review your notes on how to apply that, but again, we use this with symmetries. Again, we try and set it up where our magnetic field is constant so we can pull it out. We'll integrate over the length, and we end up with one of the simple ones that we derived was the magnetic field from a current carrying wire. Next one we're going to talk about a bit is Biot-Savart. It is unpleasant, but we'll take a look at it real quick. It is. Now you'll see it in a couple different forms. There are integral forms, there are other forms, but for the most part it looks something like this. Mu naught over, stop that, 4 pi times the quantity of our current dl cross r over r cubed. Now I'll talk a little bit about that r cubed. I think I'm missing the integral in here. Let me double check. Because we've got a dl, so we should have that. Nope, it doesn't have it listed. Oh, that's dB. Okay, so our magnetic field is equal to this. Basically, Biot-Savart is Coulomb's law, except for magnetism. Now, the problem with magnetism, and why this equation becomes so unpleasant to have to deal with, is basically what you're doing is you've got a wire, a little differential section of wire, where this is some dl. And you're looking at the magnetic field that's created from it, and then you add them up all across the wire. So you could have the wire come out and go like this, and maybe loop around, and do all kinds of crazy stuff. Because you may immediately think, hey, well, we've already got equations for the magnetic field from a wire, but that's really only when it's a nice straight wire. Not all the wires are straight. Basically, this allows you to say this little tiny differential piece has a current going through it like this, and this is the equation I would end up with, and then I would add all of those up. It's effectively like having a point particle, just like Coulomb's law. The problem is, it's difficult to get a current going through a simple point. Yeah, you have currents going through points all the time, but the current itself is a continuous thing. It's coming from over here, it's coming through here, it's going through all these different points. We can't just have it sit at the one point. That's not how currents work. So normally, they're in a combined larger piece. Normally, when you're looking for the magnetic field, you're either going to use some of the other equations that we've dealt with, or you're probably going to use Amperes Law, because this guy's a bit of a nightmare to deal with. Now, one of the final things that I will say about this is this r, in the way that I've drawn it with this r cubed, which you may have seen, we're like, wait, but Coulomb's law is r squared. This r is the total vector, which means it has both the magnitude and the direction. So we put an r cubed on here so that we've got the magnitude cubed down here, and that will have one of them cancel out with the magnitude up here. This is the same thing as saying r over r squared, where this is a unit vector. It has no magnitude. It has a magnitude of 1, I should say. These are both saying the same thing. So this magnetic field still drop off as 1 over r squared, the same that we see with the electric, but it ends up with this way of writing it. It may look a little bit different. Again, you very rarely actually apply this specific thing because it gets unpleasant. But you could go through and you could find, hey, this is a differential piece and we could integrate along this. However, for the most part, you're probably going to be dealing with some symmetry and you'll end up with Amperes Law. For the most part, whenever we're dealing with currents, they're often going through wire. Okay, so pay no attention to the fact that I appear to be wearing different clothes and suddenly more of the board is filled in. It's not like the camera actually ran out of power partway through filming this. I have now recharged the camera and we are ready to pick up where we left off. So, about the point where it cut out was when we were talking about Biot-Savart. So, I think we managed to finish all that and we were just about to jump into magnetic flux. So, let's talk about magnetic flux. Main equation we have here in the calculus form is our magnetic flux phi equals the integral of B dot dA. Now normally this is oftentimes going to simplify down to the simpler equation where our flux is equal to B dot A, and then that's a dot product, so we would have that simplified down to the cosine of the angle between them. Keep in mind that this is once again an area vector. And so with an area vector, it's the one where it's at a right angle to the area itself, so that if I tilt the area slightly, I can take that into account to find out how much flux I have through it. Now, the reason that they have an area vector, something that's at a right angle, is again, if I had just pointing along one side, I could rotate it freely about this, and my vector would still point the same way. So I could end up with zero flux, like with the light up there, and it's pointed the same way as this, which would have total flux on there, all the flux I can get, effectively. The same thing with this guy. I could have it like this, or this. And so to have one vector that keeps track of exactly where this guy is pointed, we've come up with our area vector, which is at a right angle. So we have a dot product there, simplifies down to the cosine of the angle between them, but remember the angle for your area is your area vector. Now, one of the cases where the integral form will come up, phi equals the integral of b dot dA, is if you have something like, say I've got a loop of wire, a rectangular one here, and maybe I've got a magnet over on this side where the magnetic field is actually getting stronger as I get closer and closer to that magnet. So I've got here the magnetic field a function of this displacement in the x direction. Now my area is going to be the total length of this x times y here, and that's my area, but I'm going to find that my magnetic field changes, say, as a function of x. It's getting stronger as we go. We could say arbitrarily that it's 3x plus 2. And so what I would do is I would now come into this. I would say from the changing magnetic field's viewpoint, this y value, that's a constant. It doesn't matter with each of these here and here and here. It's not changing with respect to y, so that part of the area, maybe some L, is constant. So what I'd end up with is I'd find phi is the integral of the function for my magnetic field, in this case it's a function of x, times y, and then I'll integrate all along x, dx. So here I have dA is equal to y, my height, times dx, some differential length that I'm going, and that gives me little bits of area that I then integrate. I add all the way up, and I come up with my total flux. And then I just carry this through. Y is a constant, so it gets pulled out, and I execute my integral, and I'd end up with, this is the equation for my flux. Now, one of the things that you could do with this is you could turn around at the end, and now that you've got a function for your flux, although this is a function with respect to displacement or position, you could then also bring in your EMF, your electromotive force, which for all intents and purposes is effectively equal to a voltage that is pushing charge around in a circuit, and that'll be equal to negative d phi dt. Or now we could take this and we could take the time derivative of it, although with this particular example I have no time dependence on it, so that would end up being 0. I would need something where this guy is changing with respect to time. But we could do the same thing with this. We could have a magnetic field that changes as a function of time. Although stitching both of those together in one problem is unlikely because that would require multivariable calculus. Now, let me double check. Is that where we ended up? Pardon me. So, one of the final things to keep track of is when you're looking at the change in flux with respect to time, you'll have this relationship here where your electromotive force is equal to this, your change in flux, negative your change in flux with respect to time, mostly because the current is going to be induced in such a way that it's going to try and keep things from changing. The universe does not like change, and therefore, if you have a decreasing magnetic field, maybe it's going too far away or just becoming less powerful, you'll actually induce a current that will try and reinforce that magnetic field in there so it doesn't change. That current will be driven by this electromotive force. Often it's our little squiggly E. And for all intents and purposes, it is used as a voltage, right? So you'll have it going through a loop of wire or a circuit of some kind. And so this would effectively give you your voltage. You can imagine a voltage source being put in here. Now technically the voltage source is kind of spread out through the entire wire, but that's how you would end up using it, where this is equal to your voltage, so then you could set it up as your voltage for any of the circuits that you're playing around with. That's the simple yet effective approach on that. One of the final things to talk about is the concept that potentials electric potentials are always defined, in fact I'll do the little define thing, as 0 at infinitely far away. Okay? So whenever you're doing something like calculating the capacitance of a given shape, so I'm not certain that's one we talked about, so I'll go ahead and do that. So something that you might encounter is having to find the capacitance of a couple of concentric spheres or something like that. You would use Gauss's law to find your electric field, say in between these guys. So Gauss gets you the electric field. Then you use your relationship that your potential is equal to negative integral E dot dx, or R, basically just a position over space, and so we would integrate across this, for instance. That would get us our voltage. And then finally you use the capacitor equation, where our capacitance is defined as the charge on the capacitor divided by the voltage across it. You'll have your voltage here, and actually from Gauss's law, you'll probably have the charge contained within. And so you move things around until you've got it in this format, and you should end up with your capacitance. Now the final thing, and the reason I bring this up now, is when you evaluate your potential to find out what it is, you have to compare that to your 0 mark is technically infinitely far away. So when you evaluate this integral, you may have to play around a little bit with the limits of integration or the constants that you end up with, such that this is satisfied. But again, that's one of the definitions to keep track of. Okay, that should be the majority of it. Biot-Savart, as we talked about up here, complicated. It's a very thorough way of going about doing things, but it becomes very difficult to actually evaluate the math in and of itself. So it's not something that is done on a regular basis. Usually when you're looking for the magnetic field, you're going to rely on Amperes Law.